Alright, then welcome back everyone. Let's solve this question extremely round. So I guess this is the second last question of the series. If you are following the playlist, please like the videos. Okay, because I'm lately seeing a lot of less likes in the videos. Anyway, so let me read out the question for you. Let's call a positive integer extremely round if it has only one non-zero digit. Okay, so a good basically integer, positive integer is called extremely round if it has only one non-zero digit. For example, 5000, 4, 1, 10. They all have only one non-zero digit. That's why they are called extremely round integers. However, these are not because they have more than one non-zero digit. We are talking about positive integers, by the way. Okay, only dealing with positive ones. Okay, you are given an integer n. You have to calculate the number of extremely round integers x such that x greater than equals to 1, x less than equals to n. Fine. So the question is simple. We have given a definition. They have given us a definition of extremely round integer. Basically, an integer which has only, you can say, a non-zero digit present once, and we have to calculate a number of extremely round integers x such that it is less than equals to n, greater than equals to 1, less than equals to n. Fine. So, and the input is simple. They have just given n. Okay, they have just given n which ranges from 1 till, this is I guess 1e7 minus 1, right? n plus n minus 1, because there are 6 nines if I'm not mistaken. Yeah, 6 nines. The description of ith test case is this. Fine. So we just have n and we have to find out how many extremely round integers are there greater than equals to 1, less than equals to n. That's what this question is all about. Yeah, so there's not much substance to this question again. So let's try to make some observations. So what are extremely round integers, right? Integers, positive integers basically, which have only one non-zero digit, right? So let's just see. First of all, like this is fine, right? 1 to 9 will be extremely round integers, right? 1 to 9 will be extremely round integers. Then, we'll have 10, then 20, then 30, then 40, so on till 90, right? So these are extremely round integers. And let's talk about 3 digit. So basically what I'm saying is the range is here 1e7, right? So I'm just trying to see how does the round integers look. Basically that's what I'm trying to see. Then 100, right? 100 is extremely round. Then is 110 extremely round? No, 110 is not. 200 is extremely round. Okay. Then 300 is extremely round. So on. 900 is extremely round. Fine. And what about 3 digit? Well, these are 3 digit extremely round numbers. What about 4 digit? Because in the end you'll have to go till, I guess here 6 digits only. So till 3 digits we figured out. Let's see about 4 digit extremely round numbers. Here they are like 1000, right? Then 2000, 2000, 3000, 4000, so on till 9000, right? Fine. What about 5 digit round numbers? 5 digit extremely round numbers. It will be 10,000, 20,000, 30,000, 40,000. So you're seeing a pattern here. You're seeing a pattern here that if I talk about extremely round numbers from range 1 to 9, there are 9 of them. What are those? 1 to 9 basically, right? So if I write it more concretely, 1, 2, 3, so on till 9, these are the extremely round numbers. And then I talk about 2 digit extremely round numbers, that is in the range 10 till 99. Again, there are 9. So basically 10, 20, 30, so on till 90. We talk about 3 digit extremely round numbers, they go from 100 till 999. And what are those? They are also 9. 100, 200, 300, so on, 900, right? So similarly, the extremely round numbers from 1000 till 4 times 9, so basically the 4 digit extremely round numbers are also 9, which is 1000, 2000, 3000, 4000, 5000, so on. Similarly, the range that we are is 1e7 minus 1, right? So from 1e6 till 1e7 minus 1, so basically if this is 10 power 6 till 10 power 7 minus 1, again there are 9 extremely round numbers, right? So what you're observing is the extremely round numbers are very less, right? Extremely round numbers are very less, right? So it just some, like I guess if I'm not wrong, how many are there here? So 1, 2, 3, 4, then these are 4 digit, right? So these are 4 digit, so basically some multiple of 9, right? So I guess around 90 if I'm not wrong, 90, or basically very less. The extremely round numbers are very less. Observation that you have to make here is extremely round numbers are very less, right? Extremely round numbers are very less. Okay, so extremely round numbers are very less. So that gives you a hint here. See, of course, in this question, you cannot like whenever you are given n, you cannot go through like 1 to n and check whether a number is extremely round, whether a number is extremely round or not, because the constraints are pretty high. You cannot, you won't be able to run this loop like in the t-test cases, because overall the time complexity will become 10 power 4 into 10 power 7, right? Because we try to go through n every time and check whether this number is uh, extremely round or not. I'm not even checking the complexity, considering the complexity of checking whether a number is extremely round or not. That we can assume to be constant, or number of digits present in n, so we can assume that to be constant. But if you try to, in every test case, in each and every of 10 power 2 test cases, you try to go till all the numbers will 1 and check, it's gonna consume 10 power 7 into 10 power 4, so basically 10 power 11. So 10 power 11 is not a, you won't be able to do it in 3 seconds basically, right? Because in 1 second I guess you can do at worst 10 power 8 operations, right? And you should actually try that you only do 10 power 7 operations. That's also one important. Now you know that you cannot go through every possible value of like you cannot go from 1 to n and check whether a number is extremely round or not. But since you know extremely round numbers are very less, just in some order of 100, then you can pre-compute extremely round values, right? So what you can do is you can just pre-compute, all the extremely round values, right? All the candidates, basically all the candidates, and this will consume how much time? This will consume order of 1e7 time, right? Because in the end you basically just go from 1 till 10 1e7 minus 1 and just pre-compute all the candidates. You can do this. You have the time limit of 3 seconds, and of course you can run this loop. You won't be having any problem. Now what you do in every test cases, in every test cases, in every test cases, so now you have pre-computed it, right? So basically now you have a, let's say 100ish all the like very less values, but 100ish extremely round numbers at your disposal. Now just go through. So given a n for each test case, or should I write for each test case, for each test case, okay, just go through, just go through the candidates, go through the candidates, go through the candidates and just return those candidates. Basically you can just increment, return those candidates, or basically just count the candidates, go through the candidates and count which are less than n, less than equals to n, basically, and the job is done. And you are definitely sure this is gonna just consume some order of 100, or basically a constant time operation. So now you see what happened here. You know you cannot go through like go from 1 to n every time, but you also found out that extremely round numbers are very less. Extremely round numbers are very less. So what if I just pre-compute them? They were around they were constant, around 100ish extremely round numbers. So I'll just pre-compute them and store it in some map. Okay, let's just say store it in some map. And what I'll do is for every test case when n is given, I'm gonna go through my data structure in which I've stored all the extremely round numbers, and just check, okay, are you less than n, are you less than equals to n, are you less than equals to n, are you less than equals to n? If yes, then I'm gonna just increment the count of extremely round numbers. So that's the approach that you should follow. So the main intention behind this question is to let beginners get idea about pre-computation, when pre-computation is helpful. Now there can be other ways to solve this question, right? Like when I first saw this question, I solved it in a different approach, but I believe that the developing the intuition or habit about pre-computation is much better when you're starting out in CP, because a lot of questions, like even till A, B, or even C questions, rely on this idea of pre-computation. That's why you should develop this habit of pre-computation. And how did I get the idea of pre-computation? The extremely round numbers, the candidates that I was after were very less. And in basically, I don't know if you know this, in C++, you can define global arrays of size till 1e7, right? You can define global arrays of size till 1e7. So if you know that if your values, here the values are very less anyway, right? So you can pre-compute all your candidates and store it in an array, or right now here I'll basically just create a map, or that we'll see. Implementation details I haven't discussed, that we'll discuss in the coding part of the video, but that's that. So we'll just pre-compute and store all of them in a data structure, maybe a map or something, and then whenever n is given, I'm just gonna go through my entire values of extremely round numbers and check whether if it is less than equals to n, then I'm just going to increment the count. Fine. So now the time complexity, what does it boil? The time complexity is simply, okay, the time complexity is simply order of t into, for every test case I just need to perform a constant time operation c, but of course initially the pre-computation time was also there, so 1e7. So this is the time complexity of this algorithm, and yeah, that's that. So let's see how we're going to implement this.
Alright, then let's code up the solution. So let's just first pre-compute all the extremely round numbers, right? So I'll just probably create a set here. set of int because the range is from 1 to 9, 6 times 9, right? So we can store all of them in an integer. I'll just store them in candidates here. I'll go from 1 till, I guess 1 is 7 you have to go, right? 1 is 7. So 1 is 7 minus 1 basically, I plus plus. And then what I'll do is, if I'll probably create a checker here. If basically this is extremely round, if this I is extremely round, we can just store it inside this candidate, right? So I've taken a candidate set here. You can also take a unordered set, but I prefer taking set. Like usually in CP, you should use sets instead of, like, the unordered versions are not that efficient. Okay, I'll probably link a blog in the description so you can know why you should always prefer using you should not use basically the unordered ones, because they are usually not much efficient when the range is very big. Anyway, so because of the collisions, if you have studied hash table in your data structures course, you know there is this concept of collision, and these collisions are very high. Like when you have a lot of numbers, this collision becomes very high, and the average time, which it was supposed to be order of 1, it goes till order of n. That's a problem. So anyway, here, if a number is extremely round, I'm going to simply insert in this candidate. And for every n, what you can do is we can just go through the candidates. So I can just go through all the candidates, auto IT, candidates, and if this element, that is IT, is less than equals to n, what I can do is I can just increment my answer. I can maybe increment the count, that I can initialize it above. Count, right? And you know that the actual extremely round number is very less. So this everything can fit in an integer. And then in the end, I can just print out the count followed by a new line. Now there's only one thing that's remaining, implementing this checker, whether this number is extremely round or not. So let's do it. So it will be a bool function, of course. Check. It is going to take an integer. Let me just call it num. And what is the extremely round number? What is the extremely round number? Only one non-zero digit, right? So basically, I can just initialize the count here again to be 0. It's a non-zero digit count. And what I can do is I can take out the digits of my number one by one. So while number greater than 0, I'll just take out the digit, last digit first. So num what 10. If the digit is not equals to 0, then I can increment the count, and num divided by equals 10. So basically, I'm going to take out the digits one by one. So what this loop does is, let's say you have a number like this, 5, 6, 7. First, it's going to take out 7 and check whether it's non-zero. Okay, if it is non-zero, then it's going to increment the count. Then I make num divide equals to 10, then it will become 56. So next time 6 will come out. Right? Next time 6 will come out. Similarly, then it will become 5. So then 5 more 10, again 5 will come out. So similarly, so this loop, I guess this is a very standard loop. Like if you have just studied C programming, this loop you should be familiar with, right? So just to check individual digits of a number. It's a very basic C++ concept that you can use. Anyway, so this is how you get all the digits. And in the end, I just need to check whether this non-zero digit count is equals to 1 or not. If it is equals to 1, then fine, true. Otherwise, there is a problem. Right? So extremely round number are the ones in which there is exactly one non-zero digit, right? So not less than that, not greater than that. So this is fine. We go through every digit, and if the non-zero digit is encountered, increment the count. Now if it is a extremely round number, this count will be 1. Fine. So that's the checker function. And this, I have pre-computed all the candidates. And now, whenever you give me an n, I'm just going to go through the candidates. And I know this will be a constant loop, right? This will be just an order of C loop. So that time complexity, I guess we already discussed. So let's not go there again. And yeah, let me just quickly run it. So 9, 13, 10, 19, 19 should come, right? Alright, so the mistake was that I have written for loop outside the function body. So I think you cannot write for loop in a global scope. So that's a little bit C++ knowledge there. So if I just include this part here inside this solve, then it will do the job. Okay, so you cannot write for loops in global scope. That's what I figured out. That was the issue. Anyway, now they should work. Let me just run it. Okay, so there was one more mistake. This should have been just IT. Because if you're using a for each loop, then this automatically every value is copied as IT. This is not going to be an iterator. So I cannot write star IT. Okay, so now I'll run it. Okay, that was humiliating. But anyway, 9, 13, 10, 19, 19. So this is the answer. So again, let me repeat what we have done here. We have pre-computed all the candidates. And whenever you give me a number, I'm just gonna go through all the candidates and check. If it is less than equals to n, then I'm gonna increment the count. And in the end, I just return the count. How do you check whether a number is a candidate or not, basically extremely round or not? We just go through each and every digit and increment the non-zero digit count. If non-zero digit count is equals to 1, then it's true, otherwise false. Let me just quickly submit it and see if it works. Yeah, it works. Thank you for watching. I'll see you in the next one.